Hi everyone, and welcome to part 8 of this formal logic video series. In this week I'd like to look at giving you an introduction to proof in QL. So we've looked at proofs in PL, and now we've introduced a way of translating sentences into our new system where we separate subjects and predicates, and we have quantifiers so that we can say some more interesting things. So we can still do proofs in this language, so I just want to look at how the rules from PL are applied in QL. And we're also going to introduce this week two new rules of inference, the existential introduction and the universal elimination. And then I'm going to look at some examples of those things in action and just the general the rules, the constants that we had from PL, how they interact with quantified statements. Okay, so we've already got, here are the constants we already knew. We've got conjunction, disjunction, negation, conditional and biconditional, and all of these are going to be applied in exactly the same way in QL that they were in PL. So if we have, say, a well-formed formula on one line and another well-formed formula on another, then we can write those two well-formed formulas in conjunction. And so on for all the rules. So phi and psi will still stand for any well-formed formula. It's just that in QL, well-formed formulas are slightly different looking things than they were in PL. So we just need to bear that in mind. But nothing has changed about these rules. If you want to, say, introduce a conditional, you still need a scope bar, a subproof that begins with the assumption of the antecedent and ends with the consequent. So nothing about the way that these rules works has changed. If you want to, I'm not going to say much about the workings of these rules in this session, so if you want to recap on these, then I'd suggest just go back a few of the videos and just have a look at the video specifically on that rule where we go through it in detail if you're still a bit shaky, because I'm just going to assume knowledge of these rules for what we're doing today. So let's look first at existential introduction. Now the logic behind this is quite simple. Suppose you know that Gary is happy. Well, if Gary is happy, what follows from this rather obviously is that something is happy. Right, if there is Gary is something and he is happy, so it follows that something is happy. Hopefully that's pretty obvious. Now the way that we would formalize this in QL, if we say that this small g is Gary and a big H is happy, then we'd write HG for Gary is happy. Now, to translate something is happy, remember we're going to need a quantifier, so we've got a something. So remember from last week when we were thinking about translation, something, whenever we have some or someone, something, we'll use an existential quantifier, so we'll have ex, that's the variable we'll use. And then we want to say that thing's happy, well we can use the same predicate for that. So something is happy would be there exists an x such that h x. Right. And the thought is that just as this sentence implies this, so does this sentence, this formula, entail this formula. So our rule for existential introduction is going to follow this kind of inference, and it's really quite simple. So if we've got a formula like Hg, then we can, so long as there's a constant there, we can go through that formula and replace that constant with a variable and then bind that variable to an existential quantifier, which will take scope over the entire formula. So in this case, the formula was quite short, it was just Hg, there was just one constant, so we replaced the G went to an X down here, and then we added on, we bound that with this existential quantifier. Now the thought that it has to take scope over the whole thing, so say if we had, I don't know, FA and say GB, suppose we wanted to make the same move here. Well, what do we know from this? Suppose that A is Adam and B is Brian. If we know that Adam has property F, then again we know that something has property F, and if we know that Brian has property G, we know that something has property B. So what we've got here is something like something is A, or what we could get from this is something is A and something is B, and there's kind of two configurations for this. We could end up with, on the one hand, we could get something, there exists something and, sorry, not something is A and something is B, that should be something is A and B were our constants, so something is F and something is G, sorry. So we'd get, there exists something, some X which is G, and there exists some Y, put those the wrong way around now, there's some X which is F and there's some Y which is G, or we could have, sometimes we'll see it written like this, there exists an X such that there exists a Y such that Fx and Gy. Right, so both of those look like they're valid interpretations or valid translations of this sentence. Something is F and something is G. Now, the way that we use the existential introduction rule is going to determine which one of these we end up with. So we need to think about beforehand when we're again, this is a case where if we were doing a proof, let's say we've got our scope bar and we start off on line 1, we've got FA and GA. In order to know the kind of method that we're going to use, we need to have in mind what our conclusion is, what's going to be down here. So if the conclusion is, let's say our conclusion is there exists an X such that there exists a Y such that Fx and Gy. Let's suppose that it's going to be in this configuration. Well, what do we need to do? Well, we've got a sentence up here, a formula that, sorry, that should be GB. It wouldn't really matter if it was GA, and I'll say a bit more about that in a second, that we can swap out just one of the variables in a formula, just one instance of it, but we'll leave that for just a second. Suppose that we stick with our original example, we've got FA and GB, and we want to get down to EX, EY, FX and GY. Well, what would be the step before this, we can ask. Let's always think about where we would be going. Remember that the rule we've seen is that we can, if we've got a formula, we can add on an existential quantifier to the front of that formula. So the step before Z, right, the one that leads to Z, is going to be one in which the formula at the front, this is kind of the main operator of this entire, this here is currently the main operator. Quantifiers work like negations in a way, in that they just apply to the well-formed formula immediately on their right. So the the EX here, the existential quantifier X, is the main operator of this whole thing. So the formula before this, on line Y, is going to be this formula without this. So we're going to have EY, and then, so it was FA, and we'll have GY. Right, so we've taken a step back. We've thought we have to take off the main operator EX, and that's going to take us a step back towards this. Right, so we can look and say, well, in this formula, it was the fx. The x was bound. Removing R, as well as removing the quantifier, we've got to get rid of the variable that it was bound to, and it's in the fx. So it was originally fa. So we'll go back to, this turns into that, right? Fa. Okay, and then we can just say, well, we'll just need to do the same thing again. We'll need to take off the existential quantifier again in order to get back. But if we take off the EY, we'll just be left with FA and GB, right? Because we'll have to get rid of the Y here, replaced the B by the looks of things. So we'll just be at our first formula, right? We don't actually need to write FA and GB. It's only a 3-step formula to get from FA and GB down to there exists a Y such that FA and GY, and then there exists an X such that there exists a Y such that FX and GY. Okay, so let's move this down a bit. Let's move it down to here, a bit more compact. So notice that if we were going through this, okay, let's add some lines of inference, some justifications in. So this was a premise that we had FA and GB, and what we did was we just applied the existential introduction rule to line 1 first. So we said line 1 existential introduction, because all we were doing is taking this whole formula, replacing one of the variables, right? So it was this variable here, sorry, this constant B, that we replaced with a Y, and then adding on an existential quantifier at the front of this whole formula. Remember, because we're applying it to the whole formula, the existential quantifier has scope over that entire formula. Okay, so we just changed the B into a Y, and then we added an existentially quantified existential Y to the front, and then we did exactly the same thing on this second line 2 to get to 3. So again we said, look, we've got FA here, so we'll replace A with X, and we'll bind that with an existential quantifier at the front of the formula. And again, because we're applying it to this whole formula, the whole formula on line 2, that means that the existential quantifier has scope over that entire line, so it has to go in front of everything. So I said that we could also get to EX, FX and EY, GY, but we just need to think a little more from the beginning. So let's have a look at that. So here's a new scope bar, and we start off on line 1 with FA and GB, and on line Z we want to end up with there exists an X such that FX, and there exists a Y such that GY. Now we can't get to this from FA and GB on its own, because as we've seen in this previous example, if we want to do an existential introduction on this formula just as it stands here, then the quantifier will have scope over that entire formula. Whereas here, each quantifier just has scope over the next formula, and then there's a larger the main operator of this formula is the conjunction, right? That's our main operator. And it links these two things, these two smaller formulas, EXFX and EYGY. So we need to think about how we're going to construct that. And again, this is why we always want to be starting at the bottom to think about the structure of our proof, just like we did in PL. Well, I think what this tells us is that on lines X and Y, we're going to need individually EX, FX, and EY, GY. Okay, and then we'll just do these are well-formed formulas, so we can just do a conjunction introduction on these two. Right, so from X and Y, conjunction introduction will give us this. Okay, well, where are these going to come from? Well, if we've got an FA, so we could turn an FA on its own into an EXFX. So if on line 2 we did, sorry, this is a premise, if we did a conjunction elimination on 1, we could get FA, and then for line X we could just say 2 existential introduction, and that would give, because we'd have replaced, say, look, let's replace this A with this X. Right, so, oops, far. A goes to X, and then we'll bind that that X with a existential quantifier, and we can do exactly the same to get to EY, GY. So if on line 3, if we had GB, so we'd again we'd done a conjunction elimination from 1 to get to GB, then we can just say, look, we're going to replace this B with a Y. So again, let's have this just to show where we're going. So here B is going to go to Y, and then we'll bind that to a existential quantifier, and we'll put that at the front of the formula. And there we go. So that was a slightly longer proof. So in order to get to this configuration, it's going to take 6 steps, because we first need to split up the formula at the top, the FA and GB, because otherwise whenever we do a existential introduction, it's going to end up having scope over that whole formula, just like we saw here. The first existential introduction stops us from doing anything like this, getting EX, FX and EY, GY on their own, because once we've added the existential quantifier, it has scope over this whole thing. Okay, so there's a case where we need to be careful and think about we need to think about where we're headed in order to see what we need to do with our proof. Okay, let's quickly have a look at another example, or another few examples. So let's suppose that we started off with L, A, A. Now that doesn't say la, that's A has property L to itself. Right, so that's a premise on line 1. Now there's 2 ways that we could apply the existential introduction to this. So the first way is that on line 2 we could say, well, we're going to replace every A here with an X, let's say, and we're going to add an existential quantifier onto the front. So we could end up with, there exists an X such that X has property L to itself, right, such that LXX, and that would be perfectly valid, right? So that would be line 1 existential introduction. But as well as, so what this is kind of saying is, if A has property L to itself, then there's something which has property L to itself. But as well as this, we're also saying that A has property L to A, which means that something has property L to something, and those somethings don't necessarily have to be the same thing. Right? So another way that we could write this, so let's use a blue, we could have done it in 2 steps. So we could have said, well, we're just going to change the first A, the second A. So we could have said, we'll replace this A, we'll turn that into a Y, and we'll bind that with an existential quantifier, so we'd get there exists a Y such that L a Y. Okay, so we don't need to change every instance of the constant. So don't need to swap out every. Okay, so here we just have there's something such that A has property L to that something. Now it turns out that in this case the something that A has property L to is A, right? It has it towards itself, but it's nonetheless true that A has property L to something. And then we could take that a step further and we could say we're going to replace this A, we're going to change that into an X and bind that with an existential quantifier, so we'd end up with exists an X such that, remember, we're just going to add the existential quantifier onto the beginning of this sentence. Right, this existential introduction applies to this whole formula. So we're going to get EX, EY, L, XY. And there we go, we've done an existential introduction in 2 cases. So the justification here would be would be, again, 1 existential introduction, and then this would be 3 existential introduction. Okay, so that's just to demonstrate that we don't need to swap out every instance of a constant. We could just swap out 1. And the same is going to go for if, say, we've got something like, if we'd had, so remember I miswrote this and I said I'd come back to it. So if we had FA and GA, what we could do here is, first of all, we'll say, well, look, we're going to just concentrate on this. We're going to turn it into a Y. So we'd end up with, there exists a Y such that FA and GY, just show with the blue what's changed from one to the other. And then from there, so we've just changed, we don't have to swap out every instance of A. Now we could have done, of course, we could have said, so let's just write in some justification so we can see, so from the premise, that's just going to go to 1 existential introduction. Now suppose that we could have done this, we could have said, well, we're going to swap out both A's for line 3, so we could have had E Z, and we would have had F, Z, and GZ. 1 existential introduction. Right, so that's still a valid move to just go through and change out each of the variables, every single one of the constants. Right, but we could also just take out one of them. Okay, and then of course, on line 4, perhaps we want to go back to this one, EY, FA, and GY. We could then swap out this FA, so we could then say we're going to have, there exists an X such that, so remember that again, quantifier goes at the beginning, it's going to have scope over all of this, so there exists an X and there exists a Y such that FX and GY. And that gets us to there. So look, we just bear that in mind, we don't need to swap out every instant of the constant in a formula. We can do just one at a time to get these longer formulas. Okay, but just once again thinking about how we add the existential quantifier into these sentences, we couldn't do something like this. So let's have our, so on line 1 we've got FA and let's say GA again. Suppose that on line 2 we swapped out, let's say we started in the proof and we swapped out the wrong thing. Right, so we said we did the EX first, right? We wanted to change this. Let's do that in a different colour just to make clear what's going on. Let's use a blue. So we went EX, and then here's our bracket. So we said EX, FX, and GA. Now let's suppose that what we were aiming for was there exists an X such that there exists a Y such that FX and GY. Right, that's what we were aiming for, and our first step was to do this. There was a premise. One was existential introduction. What we can't do, I mean, we've kind of made a mistake here. This first step was mistaken. We didn't think about how we were going to get to our conclusion. Because if we now want to change this variable, sorry, this constant into the variable y, what we can't do, let's write this in red so we know we can't do this, is kind of put the existential statement in the middle of what we already had. So it should be GY. Right, we can't do that. It'll be from 2. Okay, let's put a big cross here. We're not allowed to do that. Right, because when we add on, when we do this move, when we introduce an existential quantifier, it ends up with scope over the whole sentence. Right, so we're applying an existential introduction to this, right, to this whole formula here. That's what we're applying our existential introduction to. So let's move this down a bit so we can show what we would end up with. Let's move that down to there. So what we could end up with on line 4 is the following. We could get there exists a y such that there exists an x such that fx and oops, wrong colour, and gy. Wrong colour again. It was the right colour the first time. Okay, so that's what we could get to, and that would be from 2 existential introduction. But obviously these two, they're non-identical, right? They don't match, so we haven't gotten to our conclusion in this way, right? And we can't get to the conclusion from 2 just by kind of smuggling in or popping in the existential y in between what we already had here, right? We can't do that. That's not a valid move. No, don't do that. Okay, so the way that it gets applied all the time is, so in the steps from 2 to 4, so let's just write that. Quantifier goes to front. Yeah, so that's when introduced. Okay, so whenever we introduce a quantifier, it's always going to go to the front of the formula that we're applying it to. So in this case, when we introduce the EY, it has to go to the front of the previous formula. So it's this formula, EX, FX, and GA. So an EY has to be added onto the front of that. So we could only derive 4, not 3. Okay? So, that's our look at existential introduction. And it's not too hard a rule. It's just a case that wherever we have a constant with some predicate, a formula with a predicate being applied to a constant or one or more constants, we can swap out one or more of those constants for a variable and then bind that variable to a quantifier which is put at the front of the formula. That's all we've done here. Okay, so now let's move on to think about universal elimination. Sorry, universal elimination. Okay, where can we go up to? So universal elimination. And this rule is also extremely easy. If you know that, I don't know, all things let's say all things are yellow. I don't know why yellow, all things are yellow. And you know that, let's say, Adam is a thing, then you know that Adam is yellow. Right, so if we know that everything has a particular property and we have some instance of a thing, then we know that that thing must have the property if the first sentence is true. Right, so if we were to translate that into QL, all things are yellow, well, we could just have that as every x is such that yellow x. Right, so y is the property of being yellow, and obviously all things, whenever we see all things, it's going to be a universal quantifier, so ax, yx. Adam is a thing. Well, we don't really need a separate step for that. What we can just think is that the small a, the constant a, represents Adam. Okay, so Adam is yellow. Well, that's just going to be, let's actually use a yellow, seeing as I've got colours. So yellow a, right, so Adam is yellow. And the step in a proof from every x has property y to a has property y is really just as simple as that. We don't need any justification, because it kind of is the justification for writing ay, right? If we know that everything has that property, then take anything at all, it must have that property. That's exactly what we've just said. So if we have in our proof, line 1, our premise is every x is such that fx, that's a premise. Then on line 2 we can just straightforwardly write f a, right? Or this could be any variable, any constant, so that would just be 1 and universal elimination. Right, we can just make that move straightforwardly from axfx to fa. Now remember, with the existential introduction, we could change just one constant at a time. So if we had fa and gb, let's say, fa and ga, then we could go, there exists a y such that fa and gy, and then we could say there exists an x such that there exists a y such that, so that was just this example down here, right? We could just change one of the a's into a y and then the other a into an x at the bottom. With our universal elimination, we can't do that. So if we've got there exists an x such that fx and gx, if we want to, here on line 2, if we want to have used a universal elimination, we need to turn every x into whatever constant it is. So let's say we're using the constant a, and it's got to be every x, right? So we couldn't just do, we couldn't say, I don't know, we'll put a dot here so we know this isn't a real step. In fact, we'll put a cross here so we know that this isn't a valid step. We couldn't go AX, FA, and GA. Right. Again, let's just write no, so we know we can't do that. Sorry. So FA and GX. We'll need to take out both of these. They both have to go to an A at the same time. So on line 2 we could write FA and GA because we've replaced each variable, each constant with this variable, and we've removed the universal quantifier from the front. Okay, so there's just something to remember, that with the universal elimination rule, you have to swap out every instance of the variable in question. Okay, so you can't just swap out one, you have to swap out every single instance of it in the formula in which it's being applied. Right, so in this formula there's 2 instances of x, so both of those instances need to be swapped out. The next thing to take note of with the universal elimination is that the universal quantifier that we're eliminating must be, it's got to be the main operator of the sentence. So suppose we have AX, AY, F, X, Y. Okay, so every X is such that every Y, that for every Y, X has property F to Y. Right, so everything has this property to everything else. Now in this case, it's the AX which is the main operator, and that has scope over all of this. Okay, so we can only do a universal elimination on the X in this bracket, right? What we can't do, so again let's have our cross, we'll say no. What you can't do is write AX F X B or something, right, where we've tried to swap the Y here for a B. Right, we can't get rid of this first. So that would be an appeal to line 1 and universal elimination. That'd be clearer. Elimination. We can't do that because the AY that we're trying to eliminate, that's what we've done here. We've eliminated the AY. We can't do that because it's not the main operator of this sentence. So what we can do is, all we can do if we want to use a universal elimination is eliminate the AX because that's the main operator. So we could end up with AY F A Y. And so we'll swap out every X that appears and replace it with an A. That's what we've done here. This down to here is A goes to, sorry, X goes to A. And then of course, then we're in a position that on line 3 we can get rid of our Y if we want to do another existential elimination, sorry, universal elimination. Then we can do that and receive F A B. The skip from here is that every Y goes to a B. Okay, so there's just something to, again, to bear in mind. So let's write that down here. To do universal elimination on let's say ax, let's say a phi, must be main operator. In other words, it must be at the front. Okay? So just bear that in mind, that you can't do a universal elimination in the middle of a formula. So similarly, if we had this, suppose on line 1, so we've got every x is such that if fx, then for all y, let's say we've got for all y, L, x, y, whatever that turns out to be. We can't do anything in terms of universal eliminations with this. So again, our kind of no step is to go like this, then LXB, let's say. So the step here is to turn y's into b's. We can't do that because the universal statement that we're trying to eliminate here is not the main operator of the formula. This move, this universal elimination, is a step performed on a formula, right? And this formula has the main operator every x, right? So universally quantified. So we cannot get at this. Just like when in PL we had formulas embedded somewhere and we couldn't get at them until we'd done some other steps. Here's the same thing. In order to get at this, we need to get it on its own. We need to have AY as the main operator of that formula. Okay. So let's say, just say AY not main operator. Let's just write that a bit. Not main operator. Okay, so we can't take that step. Okay, and then one final thing to say about universal elimination. Sorry. So we know that we have to do every single one in a formula. We know that it has to be the main operator that we apply it to. So we, you know, again, if we're up here, if we've got ax, ay, we can't get rid of the ay first. We have to get rid of the ax first. The other thing is just about, suppose we had every x such that every y, let's say if fx, then gy. So that's our premise. So on line 2, if we wanted to do a universal elimination of 1, we'd be looking at getting rid of the ax, so we'd have to replace every x throughout this formula. So we'd end up with, we'd just have ay, and it would be, let's say we replace every x. So the step here is that all x's go to a's. So we get every y. Remember, we're going to eliminate this. So every y is such that f a then gy. Okay, so that's the step we've made. We've just applied the universal elimination as normal. Now, if we can apply that again to get rid of, suppose we want to get rid of the universal y. Take another step here. What we can do is replace every y with an a as well. Right? There's no reason that we can't replace different variables in a formula when we do this universal elimination with the same constant. So we could end up with fa then GA. Because remember, these are saying everything is such that everything is such that for everything, if the first thing has property x, then the second thing. But those two x and y's could refer to the same thing. We haven't got any identity statements preventing that from being the case. Right? We've not said that these two things can't be the same. These two things are distinct. Yeah. So when we're doing this, we can replace. Let's write that. Can replace two different variables with same constant. So that's where universal eliminations are concerned. Okay, that's in 2 steps, right? It's not like we could do that in 1 step. It's that we could get rid of the x's and turn them into a's, and then we could get rid of the y's and turn them into a's as well. Okay, so now let's have a look at a proof that involves these 2 rules. So we've got our existential introduction rule and our universal elimination. Let's look at a proof that involves them both. So let's say we're trying to prove the following sequence. We've got AY, AX, FX, and GXY. We've got EX, FX, then EY, GY. In fact, we've already got a predicate for G, so let's EY, BY. And from that we want to prove EY, BY. So we can write out our sequence in exactly the same way. These are going to be our 2 premises, so let's write those in. So the first line, all y and all x. So it should be in brackets. GXY, so that's a premise. And on line 2 we can write EX, FX, then EY, BY, and our conclusion, so on line Z, we're trying to get to EY, BY. Okay. Now we can think about this proof in much the same way that we did when we were just doing PL. So again, the thing to always do is going to be to look at the bottom and think, how can we derive this particular formula, EY, BY? Well, if we look, EY, BY is, some brackets there, that's the consequent of this particular formula. So here's just something to bear in mind, that when we've got the quantifiers like this, this is operating just like this is the antecedent. EXFX is the antecedent. So because there's no brackets around, if there were brackets here, for instance, then the existential quantifier would take scope over the whole of this formula. But as it stands, we've just got the main operator of this is a conditional, and on one side, what we need in order to get, so we're trying to get to EY, BY. That's the consequent that we're looking for. So in order to get that, we're going to need to somehow get to EX, FX. Because of the way the scope of these formulas work, and because this is our main operator, we can just do, in order to get this last step, we can just do a conditional elimination, using line 2 and line Y, and on line Y we're going to need the antecedent, so that's going to be EX, FX. Okay, so now we need to think about, well, how could we get to this? Presumably it's going to be from, well, the main operator of this now is this existential quantifier. So we're going to need to have done a existential introduction, say from line x, and on line x we could have had fa, right? The constant here, this constant could have been anything, so I'm just picking a randomly, because there's no constants mentioned up here. So long as we had fa, or any constant at all, we should be able to get from fa to this, based upon how we know the rule works. Right? We can just swap out any constant and replace it with a variable to get this, if we bind it and add the quantifier to the beginning. Okay, so now the question is, where's fa going to come from? Well, if we look up here, we've got ay, ax, fx, and gxy. So we've got an fx here. Right, so this, we might be able to turn into that. Well, how can we? We can't get at this at the minute because it's under the scope of these two universal quantifiers. So the first thing we're going to need to do is to turn this into, so let's put on line 3, we're going to need to do some universal eliminations. Let's get rid of that for the time being. So the main operator is this. Right, at the minute that's the main operator. So we're going to need to get rid of the y's first. So if we do a universal elimination on 1, we're going to end up with ax, and then the x is going to be unchanged, fx, and g, again the x is going to be unchanged, but let's change the, in fact let's write this in white, and we'll just write the changes in green so we can see how we've progressed. So ax, fx, and gx, and then it's going to be the y. Let's change that into a b. Okay, so we've swapped here, show from here to here, the y has turned into a b. Okay? Right, so now again we still can't get to the fx because it's in a formula that's under the scope of this universal quantifier. So let's do another universal elimination. So that's going to be from 3, universal elimination, and we'll end up with f, and this time we'll turn all of the x's into a's, so we'll end up with fa and g a b. Okay, so we've, again in this step what we've done is we've removed this universal quantifier, and every x has been turned into an a. So we ended up with fa and gab. Okay, well now it's as simple as just doing a conjunction elimination on line 4 to give us line 5. We can write in the rest of our numbers now. So that is 5, and then that's 6. 2 and 6 gives us that. Yeah, so once we've got fa and gab on their own, we can just do a conjunction elimination to get fa on its own. Fa can then be turned into their existing x such that fx, using our existential introduction rule, and then we can use that in this conditional, there exists an x such that fx, then there exists a y such that by, to get there exists a y such that by. And there we go, that's the end of our proof. So we can still use all of the same rules. We're still going to be making use of the constants that we had in PL. We just now have a couple of extra rules, and we need to be thinking carefully about when we can apply the rules. And the thing we need to think of is that we can only apply a rule if the symbol relevant to that rule is the main operator of that formula. Right. So now that we've got quantifiers, right, we couldn't do a conjunction elimination on 3. Let's write that in red. Right, we couldn't do a conjunction elimination because conjunction is not the main operator. Right, we have to wait until it's the main operator of the formula in order to do that. So we have to think about what's the main operator of this formula. So that kind of dictates what elimination rule you can apply to that formula, and what you're going to have to do in order to get at the contents. The more compacted contents of that formula. Right. So before we finish, I'd just like to have a look at a few little things. Okay, so I'd like to particularly have a look at the way the existential introduction works with negated formulas. Okay, so I'd like to look particularly at the way the existential introduction works with negated formulas. So let's suppose that we know that there exists an x such that fx, and we know that, we know that if GA, then not FA. Okay, so these are our premises that we start off with. Let's suppose that we were trying to show not GA. Well, of course, the way that we do that is with a negation introduction. Okay, because the negation is the main operator, the mo, we're going to need to do a negation introduction, and the way we do that is to assume the formula we're trying to negate. So we'd assume GA, and then see if that leads to some kind of contradiction. Okay, so what we might try and do from here is, on line 4 we'll reiterate this, conditional GA then not FA, that's a reiteration, of 2, and then use that to derive not FA. Now we might think that, look, if we reiterate up, there exists an x such that fx, 1 reiteration, this was 3, 4 conditional elimination. We might think that once we've done that, we've got, there exists an x such that fx, and we've got not something not having that property, so maybe we could, on line 7, write up, it doesn't exist an x such that fx. Right, so we'd get our contradiction. The problem is, let's just move to the side a little bit, draw a new scope bar. If we have a formula like this, not FA, and we want to do a existential introduction, remember that the way that that works is we first of all have to swap out all of the constants for a variable. So we'll say this is going to go to an x, and then we need to bind that x to a quantifier and add that quantifier to the beginning of this formula as it appears here. So if we change the a's to x's, we're going to get, and we keep the formula the same, remember we're going to get not fx. Let's do the x in blue so we can see where the change was. So we're going to get not fx, and the existential formula is going to come, the existential quantifier is going to come before that. Right, so we're going to end up with ex not fx. Right, so that is the way that an existential introduction is going to work, is that it's going to add the existential quantifier on before this formula. So this here, we've got here, is not a valid step. No, right, we can't do this to get our contradiction. Okay, and in fact, with the rules that we've got, it doesn't look like we are going to be able to. I mean, maybe this isn't even provable. I've not created it to show a provable formula. It's just to illustrate this fact that it is tempting to think, well, look, I know that something has this property f, and GA would lead to not FA, and those two look like they might contradict, right? So if I assume GA, maybe I can show it's contradictory because we know that EXFX, and I can derive not FA, and therefore get to not EXFX, right? We can't do that, okay? The only way that we're going to introduce that kind of formula, so let's say I want to introduce not EX FX, yeah, the only way that I'm going to be able to do that is by assuming EX FX and showing that it leads to some kind of contradiction, right? And then we can do a so that'd be MNO negation introduction. Okay, so to introduce negated existential formulas like this, like that we tried to do here, we can't do it with an existential introduction. 5. I just think it's worth really stressing that, because that is, I mean, that's a mistake that I would make when I was looking at how to do these. I would think, oh yeah, maybe there's a way through here. No, you've got to think carefully about what the main operator of the formula is, and just how these rules apply, right? If we've got any kind of formula, we're always going to be adding the existential. If we're introducing an existential quantifier, it's always going to go at the very beginning of the formula we started with. It can't be inserted, so what we couldn't have done is our x again to show that it's wrong. What we couldn't have done is kind of inserted it into here, right? Right, we can't, sorry, not there. Couldn't have inserted it in this gap here, EX, so we would have ended up not EX FX. Right, so we can't do that. That's not a valid step in our proof. Okay? So let's leave it there. Next time we'll look at the remaining rules of inference for QL and a couple more examples, and then in the final session, so that'll be part 10, I'll just go through some slightly more complicated proofs, or some longer proofs, so that we can see all of these rules working together in action.